Good morning, everyone. Thanks for having me here. I'm Andrea Gentile. For some of you who were yesterday at the Business Networking night, they had a slight preview of these slides. But for everyone else, I'm Andrea Gentile indeed. I lead the efforts in the machine learnable quantum models unit within Pasqal, the French neutral atom quantum computing company. And I'm going to tell you today about our efforts towards industry-relevant applications on our QPUs. And this is a path that we are taking in order to move our technology from lab prototype implementations down to an integrated product ecosystem. And in particular, let me give you some numbers which can explain the stage we are at. So by now, we have more than 40 between clients and partners. We are en route for 10,000 qubits, and we've already demonstrated more than 1,000 in one single QPUs. We have 55 plus patents and patent applications already submitted. And by now, we have crossed the number of 200 employees distributed worldwide. And in particular, let me highlight that we recently opened an office here in Seoul. And you can come to our booth, which is conveniently located just behind the audience, to meet some of the people who work over there. Now, the presentation is unfortunately too short to give you a thorough overview of our technology from the hardware perspective, but let me at least make a quick point over here that neutral atoms, beside the possibility to also implement digital gates, they also offer the natural evolution of the system as a possibility to implement analog control. And with analog control, you can, for example, achieve highly entangled states, quantum states, which are, for example, a key ingredient when you do perform graph machine learning algorithms. And this, in particular, can enable the possibility to make thousands of times more compact circuits compared to fully digital technologies. And for extra details, of course, you're welcome to either watch the talk from Loic on the hardware point of view or come visit us at the booth anytime to inquire more. But now focusing on the software applications, well, we really believe in Pasqal in the synergy between the technology-driven hardware and the possibility to be inspired by our customers towards solutions which are problem-oriented. Now, building on this synergy, we are exploring several pillars where we do believe that we can deliver quantum advantage in the near future. And among them, let me quickly highlight, we move from quantum simulation of physical systems to graph machine learning and optimization, down to really engineering problems like solving differential equations. And in order to do so, we do believe also in the power of an open source community that we're trying to foster with the software that we are developing. And let me highlight both Cadence, which is our high-level library for digital analog circuit simulation that you can use in particular for machine learning tasks, given the automatic differentiability which is implemented via a PyTorch integration. And on the low-level, sort of system-level, machine-level language, we can also offer Pulsar, which is a way that you can use, a library that you can use to design both the quantum registers and the pulses which are controlling them down to a fine-tuned level, which is really close to what can be implemented quickly on the hardware QPUs. There is also more, and I invite you to visit our GitHub pages in order to find out. But now, moving to the application level, we do have collected a number of industrial partners and relevant use cases which span a wide range of applications. And again, not enough time to talk about all of them, but let me quickly highlight here that we move from fluid dynamics applications, battery modeling, weather modeling, and I'm going to particularly select 3 applications for you today to dig a bit more in. The first one is a typical engineering problem, which is solving differential equations. And these are ubiquitous in fields as diverse as mechanical engineering and fluid dynamics. Now, our goal is to advance further the possibilities of the methods that are used in classical computing today, which are normally based either on spectral solver or mesh-based finite element methods. And what are the limitations of those? Well, I try to convey the idea that indeed there is nothing fundamentally wrong with these methods, but when the scale of the system is big and the mesh that you need in order to resolve, for example, turbulent phenomena gets particularly small, the modeling on classical systems becomes very quickly very complex. And you go from textbook examples, like studying the thermal fatigue in a T-junction, which can be easily solved on your laptop, down to cases like, I want to study the fully accurate direct numerical simulation of the fluid around the wing with turbulent phenomena. That becomes intractable on computers these days. Now, we got inspired by a machine learning solution, a classical machine learning solution, which is called scientific machine learning, whereby you do approximate a function, which in this case will be the solution to your problem, via the output of a neural network. And you train this neural network such that the output matches more and more closely the formal differential equation that you can use in order to model your system. You embed this into a loss, and this loss gets progressively minimized. Now, what is quantum about it is that we took the state-of-the-art classical machine learning paradigm and we moved it into the quantum realm by replacing, as a universal function approximator, the neural network with a parameterizable quantum circuit, where the weights of the neural network are replaced by the tunable parameters inside the quantum circuit. So how will this work in practice? Well, in practice, you do start with a random guess of the output of the quantum circuit, which will eventually give you, for example, the initial red curve that I'm showing over here, and as the loss, which is in the bottom graph, gets reduced via a classical routine which is coupled with our QPUs, the quality of the solution gets progressively closer to the correct one, the blue one on top. Now, to see this in action, we had a partnership with LG to study computational fluid dynamics. And I'm showing here how we moved within the course of the project from relatively early stage cases, like studying a lead-driven cavity, which is a paradigmatic fluid dynamics examples, down to arbitrary 3D geometries, and studying the velocity field of the fluid within these arbitrary 3D geometries using our paradigm, which is the differentiable quantum circuit, as we like to call it, where indeed you are differentiating the quantum circuit in order to represent all the derivatives which appear in the Navier-Stokes equations which regulate the fluid dynamics. Now, for a different example, and also in collaboration with a different Korean company, POSCO in this case, we moved to industrial process optimization. So in this case, the final goal was to study and improve, optimize, producing hydrogen from cracking ammonia. Now, in this case, the goal is basically to have a relatively simple process to optimize, whereby you do have a number of control input parameters, like, for example, the input temperature of the ammonia molecules, what is it, the cracking temperature in your process, and so on and so forth. And you are trying to optimize instead some output parameters, some figures of merit, which, for example, can be maximizing your hydrogen or minimizing poisonous emissions like the nitrogen oxides. So in this regard, you have a problem which is essentially modeled by having data rather than equations, whereby you can have a number of training points which are taken via the control parameters, and you want to maximize some of the figures of merit. Now, in this case, why would a quantum approach be interesting? Because if you're going into a highly non-convex problems where the function itself is unknown, so you have an implicit function that you cannot model mathematically, and you have a complex optimization space, maybe with thousands of different input variables, then also the classical optimization problem becomes a burden. So in this regard, we developed an ideal solution for this, which is called quantum extremal learning. Quantum extremal learning is also a variational paradigm, so it's also NISQ-friendly, and it works in two different steps. The first one is to embed the data into a feature map, which creates an input to what we call a cost QNN. A cost QNN can be understood as an ansatz that you can variationally train according to the output of your circuit in order to minimize a loss, which in this case is taken by checking the output of your parameterized quantum circuit against the data that you have available for some configurations of your system. Now, once you are done with the training phase, you freeze the cost QNN, so the variational ansatz is now blocked, it's frozen, and you do train instead the feature map, which becomes now an extremizing feature map. You are not encoding anymore the data in the extremizing feature map. You are training it variationally in order to find the extremum point, the maximum or the minimum of your problem. Now, to see again this in action, we did perform a process optimization with the goal that we had in mind from the previous slide, so indeed this ammonia cracking procedure. And you can see that already with a handful of qubits, just 6 qubits, we were able to perform an optimization onto a 2-parameter space where we are adopting 300 points for the training, and like in typical classical machine learning paradigms, we had a training set, and then we performed a test set in order to check if the generalization was good from the training, and we could actually predict well what will be the value of the output parameters in additional 80 testing points. And now, for a final example, for something completely different, let me show you how we are taking it to the sky, quite literally, and perform mission planning with satellites with a couple of both industrial and research partners in Europe, Thales and ESA, the European Space Agency. Now, in this case, the goal is a different flavor of an optimization problem, meaning in this case, we have a combinatorial optimization, and we want to optimize the locations and moving of a fleet of satellites that is tasked with the goal of taking pictures of different cities around the world. Now, as you can expect, this problem happens under a number of constraints, which are, for example, like the traveling salesman problem, not visiting again the same city twice or 3 times within the allotted time, or not having multiple satellites taking pictures of the same city within the same slot. And of course, you might need to change the priority of your goals as the mission continues, because maybe there is a sudden priority on a different city, or there is a certain cloud coverage and you cannot take good pictures of one. So you need to perform this optimization under these constraints. Now, why is that a problem from the computational point of view? Well, because if you use a single satellite, let's say the simplest case ever, right, in order to take the pictures of these cities, well, of course, the problem is very simple, but then the coverage will be limited given an allotted number of, let's say, discretized time steps. So you need to increase your fleet of satellites and move, for example, to 3 satellites over here. You can already see that, of course, the coverage increases, but also the complexity of the optimization of the problem increases, combinatorially, indeed, with the size of the system. Now, this problem happens to have a graph representation. And in this graph representation, the one that we chose in order to address this problem, the nodes are representing the mission slots, and the features of these nodes, let's say the colors for simplicity, represent instead the IDs of the various satellites which are available in your fleet. And conveniently, now you can express the constraints that I was telling you about before as the edges, which can be, for example, incompatibilities like not having the same satellite occupying the same area during the same time slot, and you can see everything on a discretized time step basis for the final graph on the right. Now, if you do this kind of mapping of the original problem into a graph problem, you can obtain your solution via a maximum independent set methodology. And now, conveniently, that's where I was going, a maximum independent set and graph problems in general are natively addressable on our architecture. So I was telling before that we can use analog control, right, in order to leverage upon the natural evolution of the system. Well, this is one of those examples. And in this case, for example, you can encode unit disk graphs using the Rydberg dynamics of our systems. And each of the green dots that you see in the middle graph will represent a position of one of the atoms which represent the qubits in our QPUs. Now, how do we obtain the solution? Well, we obtain it in different steps. So as I said before, we first represent the problem with a certain graph with the constraints embedded in the edges. We do perform the initial state preparation on our QPU, so we do arrange the atoms with the flexibility that our QPU allows us. And then we obtain the result directly from the final projective measurement as a bit string, and those bit strings are going to represent the solution to the maximum independent set problem, and therefore the actual ideal allocations of the satellites for any given time slot. Now, let me conclude with some perspectives. I know that I've thrown a lot of information to you with these slides, a lot of different problems, but what I would like you to retain from this presentation is that in Pasqal we are really struggling and making all the best possible efforts in order to deliver real-world solutions to problems which are industry relevant and which are running on our QPUs these days. So the experiment that I've shown you, for example, with the satellite, it has been run on our QPUs already these days. So they are implementable on our machine, and we are very happy to customize these solutions to further applications, further than the ones that I've shown you. And with this, 감사합니다, everyone. Thanks, everyone. And I'm happy to take questions.
Thank you very much for your speech. 네, 그러면 이제 질의응답 시간 잠시 갖도록 하겠습니다. Now we will have a Q&A session. 자, 질문 있으신 분 거수해 주시면 마이크를 전달해 드리도록 하겠습니다. If you have a question, please raise your hand and our staff will deliver microphone to you. 네, 자 여기 좌측에 계신 남성분께 마이크 전달 드립니다.
Hello, thanks for your presentation, and I would like to ask a question about the satellite constellation problem. As far as I understand, the satellite constellation problem is not quadratic problem or some kind of a linear problem. So how you make a equation for that problem?
How do you make, sorry,
The equations for the problem.
Oh, well, those are different problems now, right? So the first one for the differential equation, I was showing a different methodology which is based on the equations themselves. In this case, you have a combinatorial optimization, where instead you are modeling it as a graph, and the graph itself, so the graph dynamics, is what you are embedding in the atomic system. So in this case, you have literally a native graph representation for the problem, where, let's say, for example, the values of the edges within the graph can give you the value of the constraint that you are trying to input in the graph. So in this case, it's not an equation-solving problem where you're using the approach that I was telling in the first part, where you're representing the equations with an embedding in our quantum circuit. You are really representing the graph and the constraints within the quantum circuit natively. You are not going through an equation in the middle.
Okay, so you mean the weighting factor of the edges are variables, is it?
Correct.
Okay, thank you.
So
much.
the locations of the nodes and the values of the edges, that's what you are going to tune in order to represent your problem.
Every time the node properties can be updated.
Correct.
Okay, thanks so much.
네, 감사합니다. 다음 질문 받겠습니다. 자, 통역 서비스가 진행되고 있기 때문에 편하게 저희 모국어인 한국어로 질문 주셔도 되고요. 영어로 질문 주셔도 되겠습니다. So they can get more details on your presentation at your booth, right?
Absolutely, yes. You're welcome anytime.
Yes, it's totally welcomed. And the booth number is P04. 네, P04번 부스 파스칼로 방문을 하시면 오늘 이 발표 내용으로 확인하신 내용들 보다 깊이 있는 내용 확인하실 수 있다고 하니까요. 추후에 질문 있으신 분들 방문해 주시면 되겠습니다. 자, 그럼 이렇게 해서 세 번째 발표도 마무리하도록 하겠습니다. 발표 함께 해주신 안드레아 젠타일님에게 다시 한번 큰 박수 부탁드리겠습니다.
Thank you so much.
Thank you very much once again.